Donc aujourd'hui, on a la joie d'accueillir Richard Binzel, qui est professeur au M.I.T, au département of Earth, Atmospheric and Planetary Science. Donc c'est quelqu'un qui est très connu pour tout le travail qu'il a fait sur l'observation télescopique des astéroïdes, de Pluton, tout le travail qu'il a fait autour de l'étude ce qu'on appelle des Near Earth astéroïdes et des dangers que ça peut entraîner, bien sûr. Et tout le travail qu'il a fait sur l'étude des astéroïdes, l'origine des astéroïdes, les liens avec les météorites. Et bien sûr, le travail sur Pluton. Et aujourd'hui, il va nous parler de Pluton, donc il est co-aide dans cette mission New Horizon pour Pluton. Et donc, vous allez voir que, je ne veux pas déflorer ce qu'il va dire, bien sûr, mais je vais dire que des choses que vous savez déjà, mais vous allez voir que Pluton, c'est assez extraordinaire parce que c'est la science en marche. Donc, Pluton a été découverte en 1930, c'est la planète découverte par un Américain, la première, à partir d'observations faites à l'Observatoire Lowell à Flagstaff. Et ensuite, dans les années 50, on a un peu peur à penser qu'il devait y avoir une source pour les planètes à courte période, et donc il devait exister la simple ceinture, la ceinture de Kuiper. Et puis, en 70 ou 75, je ne sais plus, on a trouvé une moon de Pluton, qui est Charon, et puis en 92, il y a le premier, à cet effet d'Hawaï, le premier autre objet de la ceinture de Kuiper qui a été trouvé. Et maintenant, on pense qu'il y en a, je ne sais pas, plus de 100 000 qui ont des rayons de quelques centaines de kilomètres. Voilà. Donc c'est vraiment la science en marche. Hein. Je ne sais pas ce qu'on découvrira demain, et en tout cas, l'observation de Pluton est très difficile parce que c'est très loin. La lumière met plus de 4 heures pour venir, c'est tout petit. Enfin, ça fait, je ne sais pas, 2 tiers de la taille de la Lune. Et d'où la raison de cette mission, qui est la première mission à aller explorer Pluton et les objets autour. Voilà.
Merci. Et merci Marc, et merci à tout le monde pour venir. So I switch to English and say thank you for coming. We will have some 3D images. Red is on the left, rouge à gauche. Those will come in about 20 minutes. And in 2 weeks, Brigitte has invited me to give a talk at the museum on meteorites and the connections to asteroids. So if this talk is okay, you have another chance in a week. So the first thing I want to tell you is that I am just one member of a very large team that has put this mission together, and I'm going to give you a little bit of the story of the mission and how I came to study Pluto. But the important thing to tell you, this is on my car, the important thing to tell you is that this is a team effort and it's not just me. So you may have heard, and Mark said that we happen to call Pluto a dwarf planet, and any astrophysicist knows that the sun is a dwarf star, and we call the sun a star, and we love the sun very much, and so there's no reason why we should not love Pluto. And at the same time, the science that we are talking about, the label of planet or dwarf planet doesn't matter at all. It's the science that matters, so the label is not important. Okay, so I like to try to explain, especially to my students, how do you get a mission to Pluto? How do you achieve a big project? And you cannot say it is because we have never been there before. There are lots of places we have never been. There are lots of research problems we have never completed. And so I like to explain that you have to build up your case, you have to build up the reason for a mission block by block, like a pyramid, where, for example, the case of Pluto and the Kuiper Belt, there were surveys to discover objects in the outer solar system. We began to make physical measurements of what they were. Some of them proved to be very interesting. They gave us many science questions, and we used ground-based telescopes for many decades to study Pluto, but we found we reached a limit, that we could not learn anything further, and we had important questions about how does our solar system work, how does planetary formation work. And so it's for that reason that we are finally able to argue for and achieve the capstone of planetary exploration, which is usually in the form of a spacecraft mission. All right, so as Mark said, Pluto was discovered in 1930 by this gentleman named Clyde Tombaugh. And the way this works in astronomy is that you take photographs, these were glass photographic plates, that you point at the same spot in the sky over the course of several nights. The stars, of course, remain fixed in their positions, but objects in the solar system move because they are in orbit around the sun. And so Clyde Tombaugh was surveying the sky, looking for moving objects. He found lots of asteroids and comets, but also found this very slow-moving object indicating it was far away in the solar system. And this was the discovery of Pluto. In the 1980s, as I will say in a moment, I was one of the few graduate students in the world studying Pluto, so that means you get to meet the discoverer. I'm the one on the right. And Clyde died in 1997, and his ashes are on board the New Horizons spacecraft. So I was working as a summer student at the U.S. Naval Observatory in Washington, D.C. in 1978, when in the office next door was working Bob Harrington and Jim Christie. And in that office, as I came back from lunch one day, there were people looking through a microscope at a glass plate, and the glass plate showed these images of Pluto that were taken for the purpose of measuring its orbit, but the images were bad because they had these bumps on the side. There were stars in the same image, which were nice and round, and this was the beginning of the discovery of the satellite of Charon. They found many images over many years that showed this bump coming and going, and so they had to confirm whether it matched the 6.4-day rotation period of Pluto. And so they gave this problem to the youngest person in the room, and so I got to do some of the first verifications of Charon's orbit back in 1978. So this was the beginning of my connection to Pluto for almost 40 years. So the fantastic thing about discovering Charon, discovering a satellite of Pluto or satellite of anybody in space, is we can use Kepler's third law, which relates the orbital period of the satellite to the total mass of the system. And so we could solve for the mass of Pluto. This is something we did not know very much about, and there were many estimates, even initial estimates that Pluto was even larger than the Earth or more massive than the Earth. We now know that Pluto is about 1/500th the mass of the Earth. But something very interesting about the Pluto-Charon system is that if you calculate the center of gravity, the barycenter of the system is outside the physical body of Pluto. And as our geophysicist colleagues know, the center of mass in the Earth-Moon system is deep inside the Earth. But this is the only case in our solar system of a double planet where the center of mass is outside the primary body. And this is an example. We see examples in astrophysics of double stars that have the same property. So keep this double planet, or this barycenter notion in your mind, and we'll come back and see it in just a moment. All right, so something very interesting about the discovery of Charon is that we realized its orbit, as viewed from the Earth, was nearly edge-on, just like the rings of Saturn sometimes become edge-on when viewed from the Earth. We discovered that the rings of the plane of Charon's orbit around Pluto was about to become edge-on, and when that happens, we begin to see transits of Charon across the disk of Pluto. So we're all now very familiar with this because of exoplanet transits. But here it is, 30 years ago, we were doing planetary transits. And because Charon was blocking different parts of Pluto's surface every time it transited across, every orbit it would go in front of Pluto, we could match or simply observe how much the light was changing as the surface of Pluto was being blocked by Charon, and we could deduce what was the reflectivity or the albedo of the surface underneath. All the time in a telescope, Pluto looks like this. It's just a fuzzy blob. We cannot resolve what Pluto looks like, but this was a method to map Pluto's surface before Hubble Space Telescope was launched. And this is our map of Pluto, obtained before Hubble. And we discovered that Pluto has dark bands around its equator, bright regions on its surface, and we found bright poles that were brighter than the equator. And in space, it's very hard to make something bright because space, because of micrometeorites and radiation, surfaces tend to become dark very quickly in thousands or millions of years. And to see something bright means that you have to have some volatile, some compound that is going from solid to gas and back to solid phase. You have to have a phase change of something so the new deposit is bright. Just like fresh falling snow, which we see a lot of in Boston, is always bright when it first falls, and then after a couple of days in the city of Boston, it looks pretty dark and ugly. So we were seeing these maps of Pluto, and at the same time, astronomers were discovering that Pluto has methane. We're discovering the spectral signature methane, and as I'll show you in a phase diagram, we know that methane can change at the temperatures of Pluto. Methane can change from solid to gas, and so we were thinking we were seeing fresh methane ice. And even more interesting, that correlates with all of this is my MIT colleague, Jim Elliott, who we lost a few years ago, is the technique of measuring the brightness of a star when a planet happens to pass in front of it. So stars, of course, are more distant than planets. The planets sometimes pass in front of stars. And if you can watch the intensity of the star as it goes behind the planet, if the planet is, if it's like our moon, the light drops instantly. But if the planet has an atmosphere, we see the light gradually dim as the starlight goes through the atmosphere of the planet, then behind the disk of the planet and reemerges on the other side. So this was the discovery of an atmosphere of Pluto. And so we had all the pieces. We were seeing evidence of bright, fresh deposits on the surface. We knew methane was there. We knew methane could undergo phase changes. And we're seeing the gas phase of methane as well. So it means that Pluto must have seasons. It must be changing, at least over the course of its orbit. So as we begin to explore what's there at Pluto, this is nitrogen. The temperatures at Pluto are in the range of 40 to 60 Kelvin or so at the surface. And so there's a phase diagram at very low pressure for nitrogen, the phase diagram for very low pressure for methane. And you see the regime for Pluto is where you can have actually both nitrogen and methane transferring between the gas and the solid phase. Nitrogen, as you might know, is very hard to detect. Nitrogen doesn't interact with light very much. And the example is this room. This room is full of nitrogen, but it's not absorbing any of the light. And so for an astronomer, it's very hard to see the nitrogen. All right, so Pluto's orbit has many different things going on. Pluto's orbit is elongated or elliptical, and Pluto's spin axis is tipped over by 120 degrees. Earth, of course, is 23 degrees, but Pluto is tipped over 120 degrees. So that means that not only is Pluto changing its distance from the sun, but there are times when one pole of Pluto will be pointing to the sun, or the equator is pointing to the sun, or the other pole is pointing to the sun. So we have very strong, intense Arctic and tropical seasons on Pluto, and I'll say a few words about that. All right, so these occultation measurements, watching a star go behind the planet, gives you a measure of the atmospheric pressure. This was the first measurement in 1988, and Pluto was at its closest point to the sun in 1988. And interestingly, as Pluto got farther and farther away from the sun, this is a measure of pressure, the blue points are measures of pressure. As Pluto was getting further from the sun and supposedly getting colder, the atmospheric pressure was increasing, exactly the opposite of what we were expecting. And it turns out, this is work done by my graduate student at MIT named Alyssa Earle. She did a model of Pluto's atmospheric pressure based on the insolation that Pluto receives, and the fact that as the poles of Pluto begin to point at the sun, then you're getting the continuous Arctic summer, and the average insolation per square meter goes up just because you're always in the sunlight. And when you take into account the insolation processes on Pluto, we actually expect to see the atmospheric pressure go up. And so her model has a very nice prediction that in a few years, the pressure will drop. And it's a great thing as a student to have a prediction that will take 20 or 30 years to confirm. You might get a job for 20 or 30 years. All right, so the reason for telling you this is just to tell you what the story was. What did we understand about Pluto as far back as the 1980s? We understood it was very interactive in terms of transfer of solid and gases between the solid and gas states of volatiles like methane, probably nitrogen, and maybe things like carbon monoxide. We knew the sizes. We knew the sizes of the bodies, we knew about the orbits, we knew it must be having seasons. But that's it. We reached our limit. And at a special session of the American Geophysical Union, the AGU, in 1989, we had a special session on Pluto. And there were 12 speakers in the session and 12 people in the room, and we gave our papers to each other. Afterwards, we went to a dinner at a very nice Italian restaurant. And each time we got up to speak, we said, how are we going to learn anything more? And we were there with Alan Stern, and Alan Stern said, you know, guys, we need a mission to Pluto. And we were just graduate students at the time. And he said, but why not now? Why not us? And so that began our journey to try to bring a mission to Pluto. And this was a stamp that was issued about the same time in the United States. All the other planets had something to be said about them, and that was all they could come up with for Pluto. So something very interesting happened at about the same time, and that was the discovery of the Kuiper Belt itself by Jewett and Liu, and so we began to understand Pluto in context. And so as we began to make the case that we should go to Pluto, it wasn't just to explore Pluto, but to explore an entire new region of the solar system. So we began this process, and NASA was very supportive, and they gave us money to start, and we made a study, and NASA said, oh, that looks great, you're canceled. And then they said, but we have a new idea. Would you do it? If you do it this other way, we'll fund your mission. And we did it another way. That's great, you're canceled. And we did this 5 times, and each time we were canceled for one reason or another. And if you're familiar with Charlie Brown, who likes to kick the American football, his sister is always taking care of that. So this is what it felt like. We felt like we were Charlie Brown. All right, but we are undaunted. We are persistent, and we made our 6th try with called New Horizons. There's Alan Stern, our PI. This is the original proposal team, a little more than 12 people that started. We grew the team a little to get the proposal. This is a scale model of our proposed spacecraft. And finally, in 2001, we were successful. The objectives we proposed for the mission, you have to make lots of view graphs, as you know, for ESA and CNRS. We want to characterize the global geology and morphology of the surface, understand the composition of both Pluto and Charon, and there are now 5 satellites in the system. We wanted to study them all, and to characterize the atmosphere. And this is the resolution. M.I.T. is just about observable here in the greater Boston area. This is the resolution of our best cameras for New Horizons. All right, so we have multiple instruments on board. We have an ultraviolet spectrometer to look at the atmosphere, of course a radio to talk back to the Earth, but also we were transmitting radio waves through the atmosphere of Pluto as we went by to measure the structure. We have an imaging camera, a very large lens imaging camera, particle detector to look at the space environment, solar wind detector also for the space environment, a dust counter built by students, and then the instrument that I've done the most work on is called RALPH, and it is a spectrometer and a near-infrared imaging camera all in one. All right, so how do you get to Pluto and operate your instruments when it's so far from the sun you don't have solar power? How are you going to power your spacecraft? And it's, in English we would say it's a trick question, because if you go to Pluto and you need power, you use plutonium. It turns out plutonium has just the right energy output and lifetime for planetary missions. And so we start out with U-238, plutonium-238, and at the time of of course it starts out high, and at the time of the encounter, we were using about 200 watts of power to about what this projector is using, 200 watts of power to power our spacecraft. All right, so this is the Atlas V rocket for New Horizons. This is a model of the rocket, and here's the New Horizons spacecraft. And you can notice something about the New Horizons spacecraft compared to the size of the rocket. This is the upper fairing of the rocket. This is the spacecraft about to be installed. The spacecraft is incredibly small. And why is that? Well, just a little bit of physics as a reminder. A rocket delivers kinetic energy. And of course, it's 1/2 mv squared. And if you want to get to someplace that's far away, you need high velocity. And so to get the highest velocity, you wanted to keep your mass low. So the lower your mass, the higher velocity the rocket can deliver. And because we wanted to get there in our lifetimes, even though we started as graduate students, we don't live forever. So we did want to get there in our lifetimes, but even maybe more importantly, we wanted to get there in the lifetime of the instrument. The spacecraft has to still be working at the time you arrive, and instrumentation doesn't last forever either. So the first time we went to Pluto, we knew from the beginning when we first started designing these missions, it had to be a flyby. So finally, after all that, we got off the launch pad in January of 2006. We did a flyby of Jupiter on the way. We got a gravity assist from Jupiter that helped shorten our total flight time by another 2 years. Otherwise, it would have been an 11 or 13-year flight instead of a 9-year flight to Pluto. We did lots of science at Jupiter. And then we had overall a voyage of 3,463 days. Who was counting? I was counting every one of them. We traveled more than 4.6 billion kilometers. And are there any, we don't have any galaxy people here, anyone who does early universe. I like to tell the astrophysicists that we went all of 10 to the minus 10 megaparsecs. All right, so it's a direct route to Pluto after Jupiter. And remember our barycenter calculation? So here we are as we are approaching Pluto, imaging the system. We now have the system resolved. And there we see the motion of Pluto and Charon about their barycenter. This is perfect for your beginning physics class. You can sign the problem and then they can go look and check their answer. So here, New Horizons was checking our answer. All right, so here we are on final approach. Because we are a flyby, we can only go close by near one side of Pluto, and that's because Pluto rotates slowly. It takes 6.4 days for Pluto to rotate. So there was one side of Pluto that we were seeing less well than the other. And it turns out the side that I was mapping back in the 1980s, because Pluto and Charon are in a fixed orbit, they are tidally locked to each other. So the side of Pluto that was being transited by Charon was the opposite side of what we saw during our close encounter. And the geometry of Pluto is changing since 1988. Pluto's viewing aspect is tipping more and more towards the sun. The North Pole is tipping more and more towards the sun. But we can compare what our map looked like in 1988 compared to what New Horizons was seeing in 2015. So we think we got a pretty good note on our examination there. All right, so as I have said, Pluto is tipped over in with its axis. That means the orbits of the 5 satellites are also tipped over. So New Horizons was coming at Pluto like an arrow towards a bullseye target flying through the system. And so we designed our trajectory so that we could individually see as best as possible both Pluto and Charon. That's why they're lined up this way. We first encountered Pluto at its closest approach, then Charon, and then also we were going through the shadow of Pluto and the shadow of Charon, letting the sun do an occultation, letting the Pluto and Charon block the sun, or watching sunrise and sunset through the atmosphere of Pluto and looking for an atmosphere on Charon. So this is a diagram of the instruments are all color-coded. This is a timeline of what the spacecraft was doing as it approached the planet. So this is how you spend 9.5 years of flight, is you design the ballet. This is like a ballet, a choreography of a ballet, for the spacecraft to turn and point, take images, turn and point, take images with another instrument. Incredibly complex, incredibly fine-tuned, and we and all we could do is hope for the best. Because the situation is, we spent 20 years finally getting to the launch pad, and then another 9.5 years in flight, and 9 years of designing exactly what we want this spacecraft to do. The communication delay is 4.5 hours, light time travel, 4.5 hours from Earth to the spacecraft, 4.5 hours back. So it's a 9-hour transmission delay between anything we send to the spacecraft and anything it tells us. So the spacecraft had to do it automatically, robotically, completely on its own. All we could do was put on our ceinture de sécurité. And we did it. Everything worked flawlessly. Unbelievable. We did it. And not only was the spacecraft fantastic in how it performed, Pluto is fantastic. Pluto is absolutely amazing. We thought it would be new and interesting and incredible, and we didn't even begin to know how interesting and amazing and incredible Pluto is. So one thing that we enjoyed very much is when we encountered Pluto, the daughter of Clyde Tombaugh was able to be with us. And so this made some news. It was 14 juillet dernier. We did that for the French nation. You may know that when we had the Mars landing back in 2012, there were so many website hits that NASA's website was broken. And when New Horizons went by Pluto, we broke the website again. So we're very happy. And we even got the Google Doodle. All right, so remember this stamp from 1991? Today is mardi, Tuesday. A new stamp was issued by the United States Post Office. So we now have a new stamp for Pluto. All right, so I'm going to give you a tour. We're finally going to talk about Pluto. And I'm going to give you a tour of Pluto, and I'm going to tell you the names are not yet official. These are names that we use on the team, but they're subject to approval by the IAU. And I'm going to focus on this region, very famous region of Pluto, which is the heart-shaped region, which is called Tombaugh Regio, named after the discoverer. And we're going to look at certain regions on each of the edges and the heart of Tombaugh Regio, and I'll give you some description herein. So up at the upper edge of Tombaugh Regio, you see what look like flow patterns. This is nitrogen ice and carbon monoxide ice. And we see flow patterns that look like glaciers. Nitrogen ice glaciers on Pluto. And when we begin to think about that phase diagram for nitrogen, if you can just build up hundreds of meters of nitrogen ice, the pressure that you get at modest temperatures begins to allow that liquid phase, or get very near the liquid phase, such that you become viscous. And this is what's allowing glacial flow on Pluto. And the rate of flow might be something like centimeters per year. Not a lot compared to an Earth glacier, but centimeters per year. Active glaciers, the only other active glaciers in the solar system that we know of, are on Pluto. We even see things that look like nanotubes. This is Antarctica on Earth, of course. Something that looks like underlying structure poking up through the ice. We don't know if this is is connected at its base, or whether it is in fact water ice, basically icebergs, water ice, which is less dense than frozen nitrogen. These could be icebergs of water floating in a sea of nitrogen. That's fantastic. And we even see wind streaks. We know Pluto has an atmosphere, and here's evidence of the direction of Pluto's atmosphere. We think those are wind streaks. So we're beginning to be able to start thinking about the dynamics of Pluto's atmosphere. And something that's very amazing. When we look at the ice sheets in Sputnik Planum, we see things that look like convection cells, like you might see in your oatmeal. What's the French word for oatmeal? Avoine, yeah, oatmeal. So we think this might be convection cells. So you see that question mark? So we've been talking about this for many months, about possible convection cells on Pluto, and today, in Nature, today, perfect timing, we have published our results of our modeling that says these are convection cells of nitrogen on Pluto. So this is in today's paper. It was just released. The embargo was lifted last night. I was worried I was going to not be able to say anything about this today. But anyways, today's issue of Nature, we're on the cover. This is the cover photo from Nature, today's issue. And you can see these little cells, and we'll see these in 3D in just a minute. You see these things that look like convection cells. So what's going on? Well, we have to remember that all bodies in the solar system do have natural heat flow, just due to the assembly of radionuclides that are natively occurring. And at Pluto, we get 2 or 3 milliwatts per square meter, just natural carbonaceous material, about 2% of the Earth. So it's not very much to drive anything. It's not going to melt rock, but we don't have to melt rock. All we have to do is to increase the viscosity of a volatile like nitrogen. And so you can do the Rayleigh number calculations depending on what the depth of your ice sheet is, what's the temperature gradient between the bottom of the ice sheet and the top of the ice sheet, and of course the density and the gravity. And we're getting Rayleigh numbers of order 10,000, 10 to the 4 to 10 to the 6 is our estimate for the Rayleigh numbers. And so we can plot what's the limit as to under which nitrogen might start convecting. That's the red line. And it turns out that you don't need a depth of more than a few hundred meters of nitrogen ice at these temperatures that we find at Pluto that will allow a high enough Rayleigh number so that you can begin the convective process. And so we think we have convective flow in the ice here at Pluto. And again, the rate of flow from the center out to the side is maybe a centimeter or so per year. But this means that this region of Pluto is turning over, renewing itself in timescales of 500,000 to 1 million years. And so the reason we don't see craters in this part of Pluto is because the craters are getting erased on timescales shorter than 1 million years. We've yet to find a crater on the ice fields of Pluto. We see them other places. Something else in our paper is that we see the size of the convection cells. The convection cells are largest near the center of the heart-shaped region, up in here. The largest convection cells are here, which would correspond to if the ice shell or the ice layer is deeper there, you'll get larger scale convection cells. And we think the depth might be as much as 10 kilometers. And we think this is an impact basin. We think that nitrogen ice has filled an ancient impact basin on Pluto. When we get away from the convection cells, we get down in here, where this region is, where the ice is not convecting, we see other older features. We think these are older features on Pluto, and these are pits. We think they're sublimation pits. And now you can see the scale of these sublimation pits compared to the Ile-de-France. Amazing, absolutely amazing. So we see mountains on Pluto, named after explorers in the Himalayas, not presidential candidates. And these mountains are as high as 3,000 or 4,000 meters, so much like the Alps. And when we zoom in on these, we begin to think about what these mountains might be made out of, and we have to remember that at these temperatures around 40 Kelvin, nitrogen is not quite strong enough to hold up a large height under its own compressive strength, but water ice can. Water ice has effectively the compressive strength of granite when it's cooled down to 40 Kelvin. And we're going to come back and look at this in 3D, that's coming up now. At Right Mons, which we're beginning to think is a volcanic caldera, a nitrogen glacier. All right, so hold on to that thought. So one of the things I'm working on is trying to understand this latitude structure. This is what we saw back in the 1980s. And just very briefly, what we've been doing is looking at the seasonal processes on Pluto. We know on Earth that the sun can be overhead in the tropics. That's within 23 degrees of the equator. But with Pluto tipped over by 120 degrees, the tropics, or the parts of Pluto that can receive the sun directly overhead, extend almost to the poles. So the pole, almost to all of Pluto is tropical by definition of where it is the sun overhead. And so here's the region of Pluto that is in the tropics of Pluto. And then you can say, where does what parts of the planet experience long Arctic winters or summers? And the Arctic regions on Pluto extend almost to the equator. So you have a large tropical region on Pluto. In fact, most of Pluto is tropical. It's more tropical than Arctic. The large Arctic region on Pluto. And there's this region of overlap, which we don't have on Earth, that is both tropical and Arctic in terms of how it interacts with the sun. And we think these are some of the processes that are driving a lot the structure that we see on the planet's surface. So again, this is work I'm doing with my graduate student, Alyssa Earle. And this dark band is a place very interesting on Pluto. It's a place that never has an Arctic winter and never has an Arctic summer. It always experiences day and night every rotation. And we think maybe it just doesn't build up a big ice layer there except for this impact basin that's Tombaugh Regio. All right. The other thing that happens is that the obliquity changes on Earth. We know about Milankovitch cycles on Earth, which are about plus or minus 1 degree. On Pluto, Pluto's obliquity changes by about 20 degrees over about a 3 million year period. And so you can have times when the pole is pointing at the sun when Pluto is at its closest point. And we think this could give us multi-year or multi-million year climate variations on Pluto. And the best example here is what looks like a flat, smooth lake of liquid nitrogen. And so there have to be periods in Pluto's history where nitrogen can even reach a liquid state on the surface. And then once it's reached that liquid state and flattens out and refreezes, it will stay flat like this. And so we see things that look like dendritic patterns and lakes indicating that there are periods of climate extreme on Pluto that we're just starting to unravel. Right now, Pluto is in a temperate, moderate climate state, sort of like the Earth. All right, so we're talking all about Pluto. What about Charon, the large satellite of Pluto? We thought maybe it will look like a cratered body like Rhea, or maybe it'll look like an active, more active satellite like Ariel. And it turns out Charon looks like it has been active in its past. What we think has been going on is as it formed and was freezing, made of liquid water, or water, as it was freezing and expanding, that gave us this big tectonic rift, this change due to the freezing and expansion of Charon. So there was sort of a major tectonic episode in Charon's history early in its formation. And we can look at that ridge, this tectonic ridge, and we're just now beginning to try to map out what the scale of this ridge is and what the total tectonic forces are. All right, so we imaged all 5 of the moons. I won't say very much about them other than to say we've imaged them. We're trying to piece together the history of how they formed. Everything seems to suggest that it was a giant impact that formed Charon, just like a giant impact formed our moon. And we see the first spectral data have come down on Hydra, and it matches Charon pretty well. We are still receiving data from the spacecraft. We have about another 6 months or so to go to get all of the data off the spacecraft. And most of the data that's still coming is spectral data, both of Pluto, Charon, and the satellites. All right. On commence avec 3D. So if we can bring the lights down. Yes, perfect. This is the Andy Warhol moment we've all been waiting for. All right, so rouge à gauche. And if you can keep bringing the lights down, that will help. Perfect. Parfait. All right, so this is working, rouge à gauche. So we're beginning to see, and this is pretty much not very much vertical exaggeration. We're beginning to see these fresh ice deposits. We think it's methane along the rims of the craters. I have to get my own glasses working. So here you can see the Here you can see the valleys. You can begin to see the depth to diameter ratio of some of the craters. They look like they've just been punched through. They've just punched through layers of this nitrogen ice. So there are some regions on Pluto that have not been resurfaced. There are a few regions that look like they are cratered with dates going back very far in solar system history, about 4 billion years. This is an old dark region of Pluto that we call Cthulhu. And here we can see, if you can see the cursor on the right, what looks like a volcanic caldera. We call this Wright Mons after the Wright brothers. And there are a few impact craters along the edges of this feature. But it's circular. It seems to have a very deep caldera. It looks like a cinder cone. It looks like the kind of thing that might have built up from eruptions of liquid nitrogen from below the surface, building up layer by layer by layer. So that's a little bit controversial, and it's based just on photomorphology, but it sure looks like a caldera. We have no other current explanation for this feature. The size of this is probably about 50 kilometers across. Vertical exaggeration is not much. At most, it's an exaggeration of 2, but the vertical exaggeration is not very extreme. So that's an amazing thing that has us very puzzled right now. Here you can see these, on the left, you can see these sublimation pits on the left, and then impact craters that appear to be distorted in some sort of long-term flowing of the ice on the surface. All right, so now we can look at Tombaugh Regio, and in particular the Sputnik planum, where we're seeing the convection cells. I'm going to go to one more image, which I think shows this even better. There, and you may be able to tell, depending how it's working for your 3D, but you may be able to tell that Sputnik planum is a depression. We're coming down from the high surface level here, down 2 or 3 kilometers to the very flat plain of Sputnik planum. And you can see the convection cells, which are larger and brighter and freshest at the center, where we think the basin is deepest. So that's the most extensive region of convection. And then probably off to the edges, the convection was once happening but is cooled off and may no longer be active. So we're thinking we're seeing a progression in the level of activity of convection that gets smaller and smaller as the depth goes down, and as you just can't quite generate or trap enough heat underneath to keep the convection going. Totally unexpected, totally amazing. My colleague Jim Elliott, we have proposed a crater on the surface named after Jim Elliott, and this is looks like a tectonic feature that's going through the side here. And in the sides of this canyon that goes through Elliott Crater, we see evidence of water ice. We're able to see the subsurface layer of water ice that's holding up all this structure. So anything that has structural integrity has to have water ice that's the underlying support. Nitrogen ice does not have enough compressive strength to hold high topography. There's this very unusual terrain that we call snake skin terrain. When you don't understand something, you give it an interesting name. And it looks like sublimation, there's stratigraphy, there is horizontal stratigraphy or lateral stratigraphy there. We love being frustrated and confused. Nature is very good at that, and it's doing it to us at Pluto. All right, so c'est la fin de la lunette. So this is This is one of the most amazing images I think that has ever been achieved in the history of science. We are in this picture, sort of. This is a total eclipse of the sun by Pluto. And you can only see this if you're an observer on the far side of Pluto. In principle, if we had a large enough telescope, we could look at Pluto in great detail from the Earth. But we can never see a total eclipse of the sun by Pluto unless we're on the other side. And we're behind Pluto too. The Earth, the whole inner solar system is blocked behind Pluto here. Anyway, I think that's an amazing image if you just think about the vantage point of it. And interestingly, we see blue. It's the nitrogen in Pluto's atmosphere scattering the light, making it blue, like sometimes we see, even in Paris, blue sky. All right, so what's next? So we are continuing, we are leaving the solar system. New Horizons will escape our solar system and go on, in principle, forever. We have discovered one object that is very close to our path that we will go by in January of 2019. We have asked NASA for the funding to continue operations. Otherwise, we end in about 1 year. Our mission is over. But we're optimistic that we will get funding from NASA. We hope we get everything we asked for. We'll find out. Anyway, this object is called 2014 MU69. Here's the Rosetta Comet, CJ, that we've been marveled at by the amazing results of the Rosetta mission. That's the comet that we've been looking at from Rosetta. This is the estimated size, about 50 kilometers across for the target that we will go past. So just in closing, one of the things we found out, we didn't even know this, but we got a lot of media attention at the time of the flyby, and the reporters said, wow, you have a lot of women working on your mission. And we said, yeah, we hired the best people. And they said, no, you have a lot of women working on your mission. And it's almost 40%. And we didn't even try. We just hired the best people. And so in retrospect, we're very proud of that, but I can't say that we were trying to do it. It's just something is working in the demographics where you have a long way to go, certainly in the United States, and I don't know exactly in France. But we're very proud that that some things are advancing in a way that we've all wanted for a long time, and we're not satisfied. We still have a way to go, but we're still working on it. So that's a nice thing. We didn't expect that; it just happened. All right, so I'm going to close, and I'm sorry for my American perspective, but it's all about the spirit of exploration. And it's fantastic. You know, this, I'm not sure what this building is more than 200 years old, I'm sure, maybe 300 years old. 200 years ago in North America, we were just making the first expeditions across the continent. It was an expedition of Lewis and Clark, famous in American history. And I think it's amazing to stop for a moment and think about what the frontier of exploration has done, or where it has gone in 200 years. It has been from exploring across a continent to exploring across the solar system. I think that's historically amazing. I think all of us as scientists can appreciate what an amazing era we are in. We are the first generation to complete the reconnaissance of the solar system. It has happened in our lifetime. Only one generation gets to do this, and we feel incredibly lucky that it's us, that we all have done this. So many of us remember the Apollo era and what a transformative moment that was for human accomplishment. And young people don't have that sense. They don't. Apollo is just a photo in a textbook. But we got an overwhelming response from young people about this accomplishment of New Horizons. And we hope that this proves to be the Apollo moment for a new generation of young people around the world. So with that, I said at the beginning, this is a team, and our bad English spelling, but nevertheless says thank you very much. So I'm happy to take questions. We should probably use the microphone. Si on peut faire une question en français. Je dois trouver une réponse en anglais, je crois.
Yes, sir.
So, congratulations for these wonderful
Thank you.
discoveries, and thank you for the nice pictures. I was wondering, what do we know about the internal structure of Pluto?
Yeah, fantastic. Great question. What is the internal structure? We know the density is less than 2, about 1.9. So we know it cannot be just water on the inside. It must have silicates on the inside. And so you can do the calculation of what is the size of the core, assuming that you start with carbonaceous material. The core is maybe 25 to 30% of the total volume in terms of the silicate core. But that's about it. We don't have, we go by too fast to measure any gravitational perturbation, to measure any of the J2 components or anything like that. So we don't have any direct measurement of the internal structure. But when and I said start young, you can start now to make the orbiter and the orbiter mission of Pluto, for Pluto, and you can be measuring the gravitational moments, and we can go to the internal structure. It's a fantastic next thing to do. These questions are there.
Also, congratulations, really extraordinary result. I was thinking of the convection cells, and you mentioned it has a silicate interior, maybe, what did you say the percentage?
Maybe 20, anywhere 20-30% of the radius.
Is it this silicate material that's generating the internal heat that would ultimately express itself as these surface convection cells?
Well, if you, I don't know, it doesn't have to be just the silicates. But if you just start with carbonaceous chondrite-like material and forming the body, then you'll have that radioisotopic composition. So whether you'll have more heat in the core than you will elsewhere, for two reasons. One, you have more; it's denser, so you have more mass, and secondly, then it's insulated. In other words, it's just harder for the heat to get out.
The external crust, so to speak, it's mostly water, ice, nitrogen.
Right.
So I'm trying to understand how much of that internal heat-producing elements.
Less than in the core for sure. The question I thought you'd ask, but I'll say is, which we're actively thinking about, is do we get anywhere in this structure, do we get warm enough for the water ice to actually be in liquid form? And is not, we have models that allow for liquid water to exist in the sort of in the mantle region of Pluto.
For the dynamics of the rotation of Pluto, do you have estimates of what would be the precession constant for Pluto?
Yes. What, do you mean nutation?
Right,
Yeah.
That's right.
Yeah. So we have the obliquity oscillations of about 20 degrees on the 3 million year cycle, but that's as far as we go. We don't have any, second order, Chandler wobble or anything like that we've been able to measure. Oh, absolutely. We have to watch for a long time. So that's a good that's a good long-term career goal for another one of our younger members.
It's a very nice talk. Looking at your convection cell, it reminds me of orthorhombic faults we see in the sediments in the North Sea. What makes you to say that it is convection cell, not just simply deformation due to cooling of the ice or breaking up the way we do in the sediments?
So I think part of the reason why we think it's convecting cells and actually renewal is the fact that it's crater-free. Otherwise, if it had any age to it at all, then we would be seeing impact craters even at the smallest sizes. Oh,
Simply faulting and compaction of the
yeah, but
sediments which create this pores, which looks like exactly the same you see here.
yeah, I think I understand. And my point is you have to have something where the surface is being regenerated and reprocessing. So you have to have motion so that older surface on the top has to move from the center out along the edges. So you actually need flow, yeah, which I think is a different process than what you're describing.
Can you comment on whether Pluto is a planet or is not a planet?
Boo. Pluto is a dwarf planet, and dwarves are planets too. So as I said, the sun is a dwarf star, and the sun is a star. So I'm very happy to call Pluto I'm very happy to call it a dwarf planet. We have dwarf stars, we have dwarf galaxies. Why not have dwarf planets? A bumblebee is a bee. A pine tree is a tree, and a dwarf planet is a planet. So I think it's simple.
You suggest that shower has been formed from a giant impact and not a capture. Can you develop that?
Yes, so we all know about the giant impact theory for the moon's formation. And it may even be in that we can argue or we can think about how likely or unlikely the giant impact scenario is for the Earth. Certainly the models, it seems to be by far the best model we have for our moon's formation. When we think about the Kuiper Belt and think about all the objects that are out there, it seems very likely that you could have an impact between two similar sized bodies. So a priori, the likelihood is pretty good. You could get a giant impact. The things that favor it is that all of the satellites are in the same orbital plane, so that the angular momentum is the same, points to the same plane as you would get from a disk that formed around Pluto after a giant impact. And we're beginning to see, we don't have all the data yet, but we're beginning to see all the satellites looking compositionally the same. So it's just a priori our best guess, and the data coming back so far are consistent with that. Anyway, so I think that's what we can say. Of course, we don't know, but the model seems to be holding together. Oui? Oh, what is the dark matter? I didn't speak to that. Maybe we'll talk about that in Nice next week. So we have methane, CH4, and when you have methane in the CH4 on the surface, and we have methane as a gas in the atmosphere, and when you have ultraviolet energy from the sun, ultraviolet photons from the sun, they can break apart the methane molecules. So you have free carbon and free hydrogen. And the free carbon and free hydrogen can recombine into longer and longer carbon chains like ethane, and acetylene. And I'm sorry, I can't pronounce all those in French. But so we think these are longer chain carbon compounds that are broken apart, probably in the atmosphere, and then they reassemble, and then they're heavier and they settle to the surface. And then why are they the darkest at the equator and we don't see them elsewhere? The idea we're working on is that the rest of the everywhere but the equator goes through these winter seasons where it gets big ice deposits. The atmosphere mostly freezes out. You get fresh ice deposits almost everywhere on Pluto's surface, except in that equator zone, which is never in the winter. It's never Arctic. It's the never Arctic zone on Pluto. And so that way the dark material that falls out just continually accumulates and accumulates. So thank you for asking. That's one thing I had to leave out in order to talk more about convection. Yeah, we don't see CO2. We see CO. In part, it's just the difficulty of detecting it if the CO2 in this room is not interacting with the light. So you want something that is taking energy out of the visible or near infrared spectrum. And I think CO2 is a very weak absorber of light in the wavelengths we're sampling. So it can be there. I don't think there's any reason we cannot have CO2.
I read yesterday that you are linking the variations in albedo with the seasons and so on. So does it still stand?
So the question is about albedo, seasonal albedo variations.
Albedo variations along latitude.
Yeah. So we think it's holding together. I can't say we have a complete story yet for the albedo and the seasons and how the frosts come and go. The problem is trying to understand on the interval of one orbit, which is 248 years, are we gaining microns, millimeters, or centimeters of fresh deposits? And so right now we're limited to within maybe 2 orders of magnitude. We know the volatiles are coming and going, but we don't know how much of it is on one orbit timescale or on a 3 million year obliquity cycle timescale. Both are very short geologically. So if it were up to me, I would go back to Pluto. Well, I'd go back to Pluto tomorrow. I go back to Pluto in about 50 years. I have to eat a lot of vegetables between now and then. But I wish we had gone to Pluto in the 1980s like we tried. Then we could be going back in the coming decade, and we could be seeing the changes over the course of many decades. So, and I think if we could resolve what's happening on the time scale of decades, then we can begin to understand what's going on in centuries and millions of years. So the long answer is that I think there are a lot of time scales that are shaping Pluto's surface, and decoding which time scale is giving us which features is still a mystery.
I was wondering, are there any technical reasons you could have put the craft in orbit around
Yes.
the planet?
If we go back to that, the kinetic energy and mass equation, it turns out that if we put enough mass onto the spacecraft so that we had the fuel to stop and go into orbit when we arrived, we exceed the launch mass capacity of the Atlas V rocket, which is the largest vehicle available. The U.S. has a new rocket, I think the SLS, as we call it, I think has more capacity than the Ariane 5. But even the Ariane 5 wouldn't deliver. We'd have to strap 2 or 3 Ariane 5s together or something to do it using current technology. So it's going to take some other means of getting into orbit around Pluto, unless you want to have a 20-year, you don't mind having a 20-year voyage, so that instead of getting there fast, you get there slow, and therefore the velocity you have when you reach Pluto is so low it does not take a lot of thrust to land in orbit. But then Pluto's low gravity doesn't help you, because it's easy to have Jupiter capture you because it's massive, but it's very hard to have Pluto capture you. So it's natural dynamics, orbital dynamics are not helping us here. But you have to start young. Regardless what it is, start young.
How long do the instruments last that you have on?
Oh, that's a great question. So you remember the decay curve? I could flip back in the slides, but maybe I'll just try to answer. The decay curve of the power from the plutonium. So eventually we fall below about 40 watts or something like that, And at 40 watts, we can no longer keep every instrument alive. The instruments, if they get below about 20 Kelvin or 30 Kelvin or something, they freeze and they're damaged and they won't function anymore. So we will select, and that's about in 20 or 30 years, the decay curve will hit that point. And we can selectively probably devote what energy we have left to keeping things warm. So we'll probably keep the radio transmitter. That will be the last thing that we try to heroically keep alive. But the funding may kill us first. We may be killed by the budget before we are killed by cryophysics. I assure you the budget is much more dangerous than cryophysics.
And the instruments themselves, they don't fail at some point?
Oh, they'll never fail. They work perfectly forever. Yeah, at some point they become too cold to operate. It's the same problem. But, ultimately they get galactic cosmic rays and radiation damage and things will ultimately, or microparticle, micrometeorite impacts, things like that. There's lots of things that can ultimately lead to the demise of a spacecraft, many billions of miles away. Hi.
We spoke of icy regions at the planet's surface, but do you have any evidence for liquid oceans?
Yeah. Yeah, so we don't see geysers. So, for example, in Enceladus, the bright icy moon of Saturn, we see geysers. We even saw little geyser plumes at Triton, the large satellite of Neptune. We've been searching for evidence of geysers on Pluto. We see that nitrogen, what looks like a nitrogen volcano. But we don't see evidence of a liquid ocean. We're beginning to wonder as we try to model the Sputnik planet, which is the deepest impact basin on Pluto, what can we understand about how that basin has rebounded over time, the isostasy of that basin? Can it rebound? Does everything look like it was a solid that's doing the isostasy, or do we need a liquid subsurface liquid layer for the isostatic structure of Sputnik Planum? So we don't have an answer yet, but you're exactly right in terms of a question we're actively looking at.
Okay, d'autres questions? Non, mais sinon, on va encore lancer.
Merci.